All right, let's go over how to do this bar problem that I gave you for in class. You can see on my right over here, I have the picture drawn twice. These are the same pictures that I used online. I think I might have given a slightly different number to first hour. If that's the case, then numbers are going to be slightly off, but it shouldn't be too far off at all. And I'm going to get pretty similar results here. So let's go ahead and begin by just making, I know it's kind of a third sketch here, but let's go ahead and just put it on here so that I don't have to just make it super messy everywhere else. Let's make sure it's a little bit bigger you can see in here. And that one goes off that way, and this one goes straight down. Okay. All right, and then this one came off that. A little bit closer to there, actually. Those two. There it is. All right. For the purpose of our force diagram. And our goal right now is to find the tension in all three strings. First thing that we should probably do is do a force diagram. Now, I would suggest, I think I mentioned this in class, starting with this little guy right here. Why? Because if you just do a not extended force diagram, straight up force diagram of this little guy right here, what you'll see is that force of gravity down is equal to force tension up. Now, because I have three of them, I don't want to write force T tension all the time, so I'm just going to say F2 right here, but know that that is the second tension. Okay, you can kind of do these same type of things when you're doing your problems, so you don't have to write a bunch extra, just simplify kind of your denotation. And I'll do the math here real quick. Sum of forces in the Y equals 0, so F2 positive, negative Fg equals that, so F2 equals Fg equals mg, and you'll note right over here that it's 220 grams or 0.22 kilograms multiplied by g gives us an answer of, I have my answer key here somewhere, 2.16 newtons. I'm just going to go ahead and go to three significant figures, so if you have numbers slightly more specific than that, that's completely fine. Okay. Then, since that gives us actually this force right here, force tension 2, we also know that that's equal to this force tension 2 because of Newton's third law. Let's go ahead and fill out the rest of the force diagram here. Okay? This guy right here, we'll call that force 1, and this guy force 3. And I should have mentioned ahead of time why I decided to do 2. Sorry about that. The reason I did that is you'll notice that I just put them in order. 1, 2, and 3. We just have one more force here, and that's going to be the force of gravity in that particular spot. Okay, so we're well on our way. We have 1 out of 3 of the other 2 forces. So I'm trying to find this guy and trying to find that guy at the same time. So let's go ahead and probably sum the torques. Now, you can put your fulcrum wherever you want. I chose for this first problem to put my fulcrum on this guy. And the reason I chose that, okay, the reason I chose that is simply because I know this guy over here, we saw in the problem that it's 90 degrees. So I like to keep that in my problem so that I can keep that canceling happening. But if you did the other one first, no big deal. You should still end up with the exact right answers. But if we go right here, let's go ahead and sum the torques around that particular spot. So if that's that, see this guy's going to make, notice I put my finger here, this guy's going to make it rotate clockwise, which is a negative. Let's call that negative torque 2. Force of gravity is going to do the same thing. Negative torque of gravity. And force 3 is going to make it go counterclockwise. So positive torque of 3. And that's all equal to 0. I actually know force 2 and force of gravity. So I'm going to go for force 3 right now, or the third tension, which is in here. So I'm going to move this around to see the tension 3 going that way better equal those two, sorry, not tension, torque 3 going that way better equal the other two going the other way. And let's fill out this equation now. R3 F3 sine theta of 3 equals R2 F2 sine theta of 2 plus RG FG sine theta of G. Now, let's talk about simplifications. Usually this is where I do it. There is actually, unfortunately, only one. I just made mention of it a second ago. This guy is 90 degrees, but you'll notice this one definitely isn't, and this one definitely isn't. So that's going to go to 1, So to find R3, sorry, to find F3, all I do is divide that underneath. R2, F2, sine theta of 2, RG, FG, sine theta of G over R3. All right. Now, this next skill is a little bit one in and of itself. So don't lose track of if you are doing fine with this, then you're good on torque. The next part is a little bit of geometry and spatial reasoning. So let's talk about how do I get R2. Okay, let's come over here to our distance guy right here. How do I get R2? Well, I put the fulcrum at this spot right here. So R2 is this distance here, which you'll notice I don't have, but I do know that it's 23.8 centimeters to the end and 2.5 centimeters here. So I do a little bit of subtraction to find that the actual distance is 21.3 centimeters. Or let's go ahead and go with 0.213 meters. We know F2, we calculated a second ago, 2.16 newtons. And we know the angle of this guy, that angle right there being 60 degrees. So sine of 60 degrees. So this part right here is this mess right here. So now we add RG. Let's come over here for lever arm, and once again, spatial reasoning. How do we figure out the middle? Well, we know that the total is 98.8. So to get to the middle from the side, we go 98.8 divided by 2, which, if I'm not mistaken, is 49.4. Now, unfortunately, we can't use 49.4 because this is not on the end. But once again, I can take 49.4 and subtract 2.5 to get that is 0.469 meters or 46.9 centimeters. So 0.469 meters. Once again, I know the weight is, well, I didn't do this, 2 pounds. Probably should have done it ahead of time, but let's do this real quick. Let's just do that conversion right up here. 2 pounds, so I know that 1 pound is equal to 4.45 newtons, so that's 8.9 newtons. And what's the angle on that? That guy is, you'll notice, the exact same as this guy right over here, so it should also be 60 degrees. Then we divide by R3. Now, if they were right on the end, that would just be the length of the bar. But since they're not on the end, I want this distance right here, so I just take the length of the bar, 98.8, and subtract 2.5 and subtract 2.5, so subtract 5. And you're going to end up with 93.8, so we should divide by 0.938 meters. Plug that all in your calculator, and you should end up with 4.28 newtons. Okay, that's how we get that. Now, how do we do the other? Well, most of the time so far, after sum of torques, we go to sum of forces. And the reason why we've been going to sum of forces is because, for the most part, all of our bridges have been super nice and parallel, so things have been nice along the y, nice along the x. And if I'm looking over here, I'm going to be honest with you, the x and the y looks very icky. So I don't want to do that. I don't want to mess with sum of forces. You're more than welcome to. It will still end the right way if you decide to do it. But you got to do, again, a little bit of geometry to figure out exactly where it's at compared to the same spot. So I'm just going to go ahead and do the thing I've talked about a few times before, and that is move the fulcrum. Okay? And again, now that we know this guy, we can do that. Now, when you go to your homework, again, make sure that you don't move this on your picture. Just go ahead and put a 1 underneath so I know where you started. And I'm going to go ahead and place the fulcrum elsewhere. Now, my two main candidates for this, and either one will work, is I would go either here or here. Okay? I decided to go here. The reason I decided to go here is because, once again, I like that 90 degrees and I want to keep it in there because I'll get at least one canceling out. So I'm going to call this my second one right here. Okay? Now, if you want to go back and look at the first part, that's fine. I'm going to erase that work so that you can see that work in the same spot. But once again, we are going to sum the torques. All right. Now that my fulcrum is here, entirely ignore that guy. Okay? Don't accidentally think that that's there as well. But this guy will cause no torque. So let's start on the left side. This is going to make it rotate clockwise, so I have negative torque of 1. Okay? This guy is going to make it rotate counterclockwise, so it's positive, which if I'm not mistaken in the first problem, it was negative. So again, I reiterate, the sign of this can change depending on where you put your fulcrum. And this guy is also going counterclockwise, so it is also positive. Even though this one's kind of up and this one's kind of down, they're both making it rotate the same direction. And that's it. So I'm trying to get something inside of here, so we should see the torque 1, torque 2, plus torque 3. If you want, either added that over there, or I subtracted both of those and threw a negative through. But there it is. Let's go to our equation. R1, F1, sine theta of 1 equals R2, F2, sine theta of 2, plus R3, F3, sine theta of 3. Let's go to canceling. So, angle 1, nope, definitely not 90 degrees. Angle 2, nope, definitely not 90 degrees. Angle 3, yep. So I can go over here and go 1. That's why I put my fulcrum where I did. Okay, so trying to get F1, so just simple algebra here. F1 is equal to R2, F2, sine theta of 2, plus R3, F3, because that's 1, over R1 times sine theta 1. That's just these two being divided underneath. So let's go ahead and plug in our numbers. R2, okay. R2 does not stay the same in this problem because I moved the fulcrum. It's right here, which might seem a little complicated until you realize I can get to the middle really easily. The middle is simply going to be 98 divided by 2, 49.4, and then subtract this, because I know from the side to there. So subtracting that number, you should end up with a distance of 0.256, or 25.6 centimeters. 0.256 meters. Okay, times F2, which we know, 2.16. The angle, still the same angle between the lever arm and the force, is 60 degrees, plus R3. That's going to go from the, let's go ahead and move this on this picture here for right now, because I don't need it on that one. Okay, R3 is going to be right here. Well, that's going to be, let's go to the end, 49.4, and subtract 2.5. So you end up with what, 46.9? If I'm not mistaken, let's check. Yeah, 46.9, or 0.469 meters times F3, which I just calculated on the last part, but I erased. So I'll remind you that my answer is 4.28 newtons. Divided by R1. R1 is going to go from the fulcrum to the force R1, and this is kind of nice, because it works out very similarly to the first one. I'll take from the middle of the side, 49.4, subtract 2.5, and it is also 46.9 centimeters, or 0.469 meters. The angle from the lever arm to the force is that 137 right there. Plug that all into your calculator, and you end up with 7.77 newtons. Now, I'll probably show this in class, but I'll show you right now what I'm going to do. Okay, to confirm this is I've got a scale here. Where did my scale go that I was using? There we are. Okay, scale here, and I can check all of these particular answers. So I can grab this guy and replace tension with this, and you can see it's a little bit above 2. We're going to get some slightly off answers because these scales aren't perfectly, but slightly above 2, or pretty close to 2.16 there that we got in the very first beginning. Okay, and then the next problem that we calculated was, I believe, force 3. So right down here. So let's go ahead and grab hold of that, maybe, and make sure it goes in the exact same direction, and I get a little under 4. We got 4.3. Okay, and in that, a lot of that comes down for friction of this guy. And then right up here, this guy, we've done it correct, should be close to 7.77. There we are. So let's go ahead and grab hold of that, and I got, let's see here, yeah, about 8. So, math matches reality. Hooray! Hopefully you did well in that particular problem. If not, come talk to me. We can work it out.